Good morning, students. Welcome back to the yet another data structure class. In the last class, we discussed about the application of a stack. As an example, we converted an infix expression into a postfix expression using a stack. I illustrated the conversion with an example. In the algorithm for infix expression to postfix using stack, we use a stack. We push into the stack the left brackets and the operators only. The operands on the right bracket are not pushed into the stack, and only the operands are taken as an output to the output, and also the operators. When we push an operator into the stack, we use one condition that at no stage an operator having a lesser precedence be placed above a operator having a higher precedence. For example, plus and minus are having a precedence 1, multiplication and division are having precedence 2. So a plus and minus cannot be placed above a multiplication and division in the stack. That is the convention we followed there. We illustrated that with an example, and we found that stack was immensely used to convert an infix expression into a postfix expression. Also, we discussed that a stack can be used to evaluate a postfix expression. What is a postfix expression? An expression in which operands comes first and the operator comes last. A plus B is an infix expression. AB plus is a postfix expression. A stack can be used to evaluate that postfix expression. Next we go to the next idea, linked stack. When I introduced you to the stack, I told that the stack is an abstract data type in which the elements are processed in the last in, first out order. A stack can be implemented either using array or using pointer. In the last few classes, we discussed about implementing a stack using array. Now we are going to implement a stack using pointer. The advantages of having a pointer for implementing a stack is many. In the stack implementation using array, if the array is having 50 size and your stack is having only 20 elements, then the remaining 30 locations of that array will get wasted. That is one of the drawbacks of stack implementation using array. Whereas when you implement a stack using a pointer, a memory for a stack element is created dynamically. Whenever a value is pushed, whenever a new stack element has to be pushed into a stack, a new memory location is created and only that memory location is used. So if you are having some 10 elements for a stack, only 10 memory locations will be used. Conservation of the memory space, that is the advantage of having a pointer for implementing a stack that we are going to discuss now. Before implementing a stack using pointer, as I told you in the last class, you should know something about self-referential structures. Self-referential structures. Before that, you should know what is a pointer. To know something about self-referential, you should know about pointer. You already know that a pointer is a variable having the memory address of another variable. A pointer is a variable having the memory address of another variable. If P is a pointer variable having the memory address of the variable X means we say that P is pointing X. P is pointing X. That is the definition of a pointer. Such a pointer is used for self-referential structure. You know what is a structure? A structure is a data type in which multiple values of different types are accessed under a common name. For example, if student is treated as a structure, then his name could be a character information, his age is a integer information, his height is a float information, his gender is a character information, his mark in exam is a integer information. Now all these things comprise a single structure called student. These values can be accessed using the student name, student.age, you can access, student.height, you can access. So this age, name, height, mark, gender, these are all called members of that structure. Members of that structure. Now coming to the self-referential structure, if one of the member is a pointer member pointing the very same structure, then that structure is called as a self-referential structure. Simply saying, a self-referential structure is a structure having a data member uh, which is a pointer pointing the very same structure itself. That is called self-referential structure. Now you see here, this is a figurative representation of a structure. Now you see this is a structure having two members. One is a data member and another is a pointer member. Now what does this pointer member do? It is pointing another structure of same kind, and this structure is also having a data member and a pointer member. So this pointer member is pointing another structure. So this is a self-referential structure. Such a self-referential structure is used to implement a linked stack. Implement a linked stack. Now you look at this example. Here my structure type is node type. Structure type is node type. This structure node type is having two members. One member I call it as integer data type info. Info is a data member of integer data type. Now what is this next? Next is a pointer member because of this star before it. And what does this next is pointing? It is pointing the data type node type. Next is pointing node type. What is this node type? That itself is a structure. That itself is a structure. So this is a self-referential structure. Again, I tell you, struct node type. So this node type is a struct type. It is having two members. The first member is a info, its data type is integer. The next member is a pointer member. The name is next. Okay, this is pointing what kind of values? It can point node type of kind of values. What is this node type? This is the structure name. Structure name. So This is a self-referential structure in which one of the member is a pointer member pointing the very same structure itself. Pointing the very same structure itself. Okay. Now, these are some of the figurative representation of a linked stack. Now look at this. This is the first element. This is the first element of the stack, and above this we have one one node called one node having two members. One is a data member called info. This info field is having 32, and this is a pointer pointing the next node. Pointing the next node. Now this node having 32 is pointed by the pointer member of the node having 50. Isn't it? Now the node having 50 is pointed by the node having 99. So this node is having a pointer member pointing the node having 50. This is having a pointer which that is pointing another node having 32, and this is having a pointer member pointing another node 25. And what does this pointer member of this one point? It doesn't point anything. It is pointing null. It is pointing null. Now this is the first node that is inserted into the linked stack first. So it doesn't have anything else to point. So this pointer member is pointing null. And after inserting this 21, this 32 is inserted. And how it is inserted, that we will see now. After inserting this one, this becomes the top node, and this will be pointing the previous node, the node having 25. Now, after this, the node having 50 is inserted. Now, the top is moving from here to here, and this node having 50 will be pointing the node having 32. After inserting this one, another node is node having 99 is inserted into the stack, and the pointer field of this node is pointing the node having 50. Now since this is the top node, this node is pointed by an external pointer called top. External pointer called top. Okay, see what recall what we discussed about top in the linear stack. We use the variable top to know the topmost element of the stack in the array. Similar such a thing we are using. This top is a pointer variable which will always pointing the topmost node of the stack. Topmost node of the stack. Supposing I am pushing in another node having the value 100 means, first of all, I need a empty node having two members. In the data member of that empty node will be empty. So in that empty data member, I will be storing the value 100. Then I make the pointer field of the node having 100 to point to the node having 99. Then after doing that, the node having 100 has become the topmost node. So the top will be moving to the node having 100. That is how you will be inserting. So you look at this picture here. Initially, this was the very first node, so the pointer member is null. Then after this, the node is inserted. After inserting this one, the pointer member is pointing this node. Then after inserting this one, this node is inserted. It becomes the topmost node. Then the pointer member is pointing this one. Then same here. Same here. Now this is the topmost node. Then after that you want to insert a node. So further, first of all, you create a dummy node. Then make the pointer member of this one to point this node. Then make this as a topmost node. So top is pointing this node. This node. So that is how you push your value into the linked stack. The right opposite is the removing a value from a stack. Now in this picture you see here, initially the top was pointing this one, only this one you can remove. You know already that the definition of the stack. only the topmost value can be removed. Okay, if you delete this one straight away, then the connection for this one is left out. So what you have to do is, you should put a temporary connection for the topmost node. Then you should move the top from here to the next node. Then you can delete this node. Then you can delete this node. That's how you will go for deletion. Again, I tell you, see, initially top was pointing this particular node. If you say delete top means, then the link for the remaining elements also cut off. They all will become garbage. They all will become garbage. So to avoid that, what we will do is, you can remove only this one. So top is pointing this one initially. So you assign the value of top to a temporary variable, maybe temp. So now both temp and top will be pointing the same topmost node. Then you will advance the top from here to the here. Okay, now this is pointed by temp only. Now you delete temp. After removing this one, only these things are available. And now this is the topmost node which is pointed by top. That is the idea behind removing a value from a linked stack. Now we are going to implement all these things now. Linked stack operations. As in the case of linear stack, we can insert a value into the stack, remove a value from the stack, display the contents of a stack, checking whether the stack is empty or not, checking whether the stack is full or not. Okay, all these operations we are going to perform. So here I am going to use class data type for implementing a stack. So before that, I need a self-referential structure, because every member of the linked structure is a linked stack is a self-referential structure. So let me define a self-referential structure first. I call it as node type. So in my stack, I'm going to use only two members. In the linked stack structure, every node will have only two members. One is a data member, and another is a pointer member. That's what my understanding is. So I treat every member as an integer. I call the name, I give some name for that as info. Then next is a self-referential structure. So the value that is pointing is node type star. I call the field as next. Okay, then I close this one. This is the self-referential structure I need. Now let me define the class for this one. Class, I call this as stack type. Call this one as stack type. As you know already, a stack is made up of two areas. One is a declaration area and a member function area. Usually we keep that declaration area as a private one. By that way you can give the data protection. So here also I keep the data member as private access specifier. I don't have to specifically give. If I don't give anything, then by default that is automatically treated as a private. So what is the attribute? What is that data member? I have it here. Just now I told you that this linked data structure stack should have an external pointer. I call that external pointer as a top. Okay, so what does every external pointer point? See, this top is pointing the node. Okay, this node is made up of a data member and a pointer field. So this okay. So top is a pointer variable that will point node type. That will point node type. Okay. Then before that, then I give the member functions of this stack class I want. I declare them as public, and first of all I should declare the constructor. The name of the class is stack, so the name of the constructor is stack type. That you should know already. See, the name of the constructor is similar, same as the name of the class. Name of the class. So since the name of the class is stack type, the name of the constructor is also stack type, and the constructor doesn't have any return data type. Okay. Now, what is the purpose of having a constructor? It is used to initialize some of the data members. Okay, here my data member is top. So what I said is, yeah, when there is no element in the stack, my top is pointing null. It doesn't have anything else to point. So by setting top is equal to null, I can create a empty stack. So that's what I will do it now. Okay. Then we go for the other operations. I want to check whether my stack is empty or not. Is empty. I want to know whether my stack is full or not. I want to know, I want to insert a value into my stack. So I call that function as push, P-U-S-H. Okay. Either I can have some formal parameter here itself. I can do anything in any way I want. Okay. Let me have a formal parameter whose type is integer. Similarly, let me have pop operation. Void, I call it as pop. Now this pop is going to return something. So I call it as int reference. So what does it meaning? After this pop function is executed, the value of this formal parameter is given back to the corresponding actual parameter. Because of this operator, the value of this formal parameter will be given back to the corresponding actual parameter. You should know what is an actual parameter, what is a formal parameter. Parameters used in the function headers are called as formal parameters. Parameters used in the calling point of a function are called as actual parameters. These things you should have known already from your first year C language. The same thing is here. Okay. Then I want to display. Void display. That's all. And display. So these are the operations that I want to do in my linked stack. Now I have already defined what is this one is. Now I am going to implement what is this is empty, what is this is full, what is how to push a value into the stack, how to remove a value from the stack, and how to display the contents of a stack. Okay. Now let me check whether my stack is empty or not. Now is empty is belonging to the class stack type, and it returns void. It returns integer. It returns integer. Now, what are the statements? When do you say the stack is empty? When the stack is empty, the external pointer top is pointing null. It doesn't have anything else to point. Even if there is only one element, then that one element will be pointed by this external parameter top. Okay. Now, when the stack is created, nothing was there. So how to know whether my stack is empty or not? By probing what does the external parameter top is pointing. External pointer top is pointing, we will know whether the stack is empty or not. Simply saying, if top is pointing null, you can claim that the stack is empty. Otherwise, it is not empty. So, return this is a conditional equality operator. So what does it says? If top is equal to null, it will return the value 1. Otherwise, it will return the value. If top is not equal to null, it will return the value 0. By this way, we are implementing the isEmpty function of a stack. So it will tell you whether stack is empty or not. Okay, next function is checking whether my stack is full or not. Okay, so you can keep on adding values into the linked structure. Where is the limit? In the case of linear stack, the size of the array is the limitation. Okay, if the size of the array is 100 means, then you can have a maximum of 100 stack elements, not more than that. But there is no such restriction in the linked stack. You keep on creating a memory area for a stack element dynamically. Then how to know whether my stack is empty or not, full or not? Only the memory device that you are using, maybe your pen drive to store the elements of the stack, or your disk to store the elements of your stack. That is the thing. Okay, only if your memory device is full, you can claim that that particular linked stack is full. Now, how do you know whether whether the memory device is full? In your memory device, if you are not able to create a memory space for a pointer variable, then you can claim that your stack is full. If it is not possible for you to create a memory space, for example, I am conducting to a class of 50 students. The particular class can accommodate only 50 students. Then one more student is coming, means I am trying to find a place for that boy. I find that there is no place for him to accommodate that new boy. Then I will say that, oh boy, this classroom is full, there is no place. Like that, the same condition is here. If it is not possible to dynamically create a memory space for a pointer variable, then you can say that your linked stack is full. That implementation we will discuss in the next class. Okay.